Alright guys, let's approach this one just awesomely and carefully. I should say awesomely but cautiously. It's gonna get a little weird, but it's about to get really awesome because this is one of the coolest things in existence, one of the trippiest things in physics, in my opinion, which is magnetic induction. So let me, for instance, just present it this way. There's two ways you can, well actually there's a lot more than two, but there's two ways I'm going to present it. Let's first recall what flux is. So flux is defined as the field going through, so we want to write the perpendicular, reminding us that we need it to go through an area. Okay, easy done. Let me draw a box. So I want a box. This guy needs a box. Super special equation. It turns out that if you, so I will actually write flux B for magnetic flux, because you can have flux of anything that is moving through an area you can consider a flux. So let's specifically say flux of the magnetic field. So it turns out that if you change the flux through an area of a loop wire, it actually induces a current. It's amazing. So for instance, I'm going to illustrate this with an example. So if I have a loop of conducting wire with no current running through it, and I start off with a magnetic field of 0. So there's just a loop of current. That's all that there is. Just a loop of current, or sorry, a loop of conducting wire, no current, no field, nothing. Just nothing going on. So it turns out that, let's say in a matter of a second, so let's say this is just a 1 meter square, though the numbers don't really matter now. Let's just do concept that I flash 2 Teslas coming out of the page. All of a sudden, there's 2 Teslas coming through this. I have now changed the flux, clearly, right? The initial flux was 0. Now the flux is 2 Teslas times 1 square meter, of course, just field times area. Look what happens. You get flux now. So what actually happens is, I'm going to draw green. The current says, I don't like that. This is the coolest thing ever, guys. The current actually creates an induced magnetic field. So be really careful, guys. The red dots were not created by the current. The red dots, so the red magnetic field is what we call an external field. So I'm going to write EXT for external. Not caused by the current, not caused by the square. By current in loop. What is caused by the current in loop is the induced magnetic field, which is in green. This is created by the current in the loop. This one is not. In other words, I had to somehow create these dots. Clearly, if I did have some other current somewhere in the vicinity, or I just had a north or south pole magnet, I hope you guys see and have seen over the last week, there's a lot of ways to create a magnetic field. Right? So I could have maybe had another loop around this. That would be a good way of doing this. If I had a loop around this, inducing that magnetic field, the point is that it would induce a current in this wire such that the induced magnetic field always opposes the change to the flux. So the induced magnetic field always opposes change in flux. So I hope you guys are cool with this notation. That's delta, that's change in, and this is magnetic flux. So this is the whole point, guys. The induced magnetic field direction always opposes change in magnetic flux. So you can then infer from the right-hand rule, so let's all do the right-hand rule here. How do I get a field going into the page here? Well, clearly I need it to come out here, circle in here, so my thumb has to point to the right here, my thumb has to point down here, has to point left here and up here, or you can use the shortcut and simply point your thumb into the middle of the page where the green is, and your fingers will curl in the direction of the induced current. This is how you generate electricity, guys. You change a magnetic field through a loop of wire, and the loop of wire will fight back. It will create a magnetic field in the opposite direction that the change in flux occurred. This is called Lenz's law. Oops. He spells it cool. He spells it, what is it? Lenz's law is this. Lenz's law says that if you change the flux through a loop of conducting wire, it will induce a magnetic field to oppose that change in flux. And therefore, of course, to do that, it creates a current. That's it. Turns out there's an equation for this, that the induced voltage, the equation involves the voltage, is negative, of course, for opposite direction, change in flux over change in time. So if you do it quicker, it actually creates a quicker moving charge, which makes sense. If I did this in 2 seconds, of course, you would get 2 over 2, so you'd get a voltage of negative 1 volt. Negative just meaning in the opposite direction to what you've done. Let's do a problem with that. Let's do that. So, magnetic flux example. So the induced voltage is the change in flux over the change in time. So there's lots of ways to do this. I'm going to do it 2 different ways. One is I'm going to have my square current. I'm going to literally put numbers to the example that I just did. Oops, right, we don't want current at first. I always do that. That's instinct to draw those arrows. So this is the before, and this is the after. So initially we want 0 magnetic field, and then we'll call that B1, and then B2 we want, I'm just going to make up a number, 2.0 Tesla coming out of the page. And I want to do that in 2 seconds. What is the current induced in the wire? Well, the direction of current, of course, will be to oppose the change in flux. And if we put our thumb in, or if we do the right-hand rule for all 4, we get, of course, it's going to go clockwise. So we get a clockwise current. Clockwise current. And our actual induced voltage will be the change in magnetic flux. So the initial magnetic flux was 0. The final magnetic flux was 2 Tesla times the area, which is 2 Tesla square meters. So we get 2 Tesla square meters over 2 seconds, which was the amount of time it took to do that. So we get 1 volt. So I'll say negative 1 volt, but remember the negative just means it's in the opposite direction, right? It's like Newton's third law. That negative just means opposite direction. Cool. This is a trippy thing. Isn't this cool, guys? This is so cool. So let's say, okay, that's problem 1. Problem 2, let's do the exact same thing in a faster time. Let's do it in 1 second. So if you do it faster, what's going to happen? If you do it faster, you're going to generate more current in the same direction. Still a counterclockwise current, but here the V induced will be -2 over 1 second. And it's cool because a Tesla meter squared per second is a volt. So that's pretty wicked. That's so weird. Right? I'm sure we could really introduce that conceptually through all the equations we know, but I'll skip that for now. Notice you get more voltage if you do it faster. Okay, example the third. Let's change the area. So what I'm going to do is I'm going to rotate my area. So let's say that I have a magnetic field going this way, and let's say it has a value of 2 Tesla. And I have a circular area. Let's have it go through this way, and like that. There we go, some artistic value right there. Right, so I want it going through the circle. And what I'm going to do is I'm going to rotate the circle such that the circle is now in the plane of the page. So I apologize if this is hard to draw, but I want to rotate the circle along this axis such that the circle is now being rotated along this axis such that here it's all the flux is going perpendicular to the area, and let's say it has some area A here, such that area is, I know it's a circle, but let's not involve pi. Let's say, yeah, let's involve pi. Let's say the radius is 2 meters, so the area is 4 pi square meters. Okay. Pi r squared. So here, the area A2 is going to be the same, except that the field is no longer perpendicular. Cool. So the flux here is going to be the field times the area, which is going to be 2 Tesla times 4 pi is 8 pi Tesla meters squared flux, because here the field is all through the hoop. You guys see what I'm doing here with the 3-dimensional hoop? This 3-dimensional hoop is kind of perpendicular to your screen right now, and all these field lines are going through it. But if I turn the hoop, boop, sideways, now, oh no, what happened? And let's say that I do that in half a second. So it takes me half a second to turn it, just a half second turn. Turns out that's going to generate electricity. So which way is it going to generate electricity? Well, it's certainly, if you can imagine, right, this side here, if I turned it this way, has now become this side here. So I'm going to color code the circle here, so it's consistent. So this side here is the same as this side here. So the field was once going through the hoop almost as if it were x's. So it's almost like this started off as x's and now it's 0, which means that the change was removing the x's, which means that the current is going to now want to add x's. So you might be like, what did you just do? You might be like, wait, what? Let's take it slow again. So these were moving into the hoop. So I could redraw this first scenario A1 as this. I could redraw it as my hoop as if my eyeball were here. So if my eyeball were here, this is my eyeball here, this is an eye. So my eyeball's here, I'm looking this way, I would see this side like this, So you got to think three-dimensionally, and I would see x's. Here, the field is moving to the right, not through the hoop, right? These lines are just overlapping this, parallel, not perpendicular to the hoop. So therefore, it's like I removed the x's. So if I were to finish my drawing here, A2, same area, of course, but I rotated it such that the B field is 0. At least the perpendicular B field is 0. Here, the perpendicular B field was 2 Tesla. So I've removed the x's. So the current is going to be like, hey, man, I want those x's back. What are you doing? And it's going to then create and induce a current to make those x's come back. Because the change was to remove the x's. And Lenz's law says that the current will always react in the opposite way of the change. So that's the whole point, guys. Whatever the change did, so if I added x's, it would add dots. If I remove x's, it adds x's. If I added dots, it would add x's, like in the previous problem. You guys see what I'm saying? It does the opposite. Awesome. So, x's inside, put your thumb in. That is a counter, sorry, that is clockwise. That is how a clock goes. That is a clockwise current. So flux 2 is 0. So my V induced is going to be negative change in this. So notice how the change is going to be negative 8 pi over 0.5 seconds. 8 divided by 0.5. I hope you guys are cool with that. 8 divided by a half is like multiplying by 2. You're going to get 16 pi volts. Notice how the negatives cancel, which confirms that if it once was x's, this is going to create x's because we took the x's away. I want that to make most sense. That if we take the x's away, it was coming to the right. We took that away, so this is going to induce a current counterclockwise to then make it go. The magnetic flux actually come back because it missed it. It said, I want that the same way that it was. So it always creates it to keep it the same. The magnetic flux in the universe wants to stay the same, and currents will be induced to make sure that happens. Welcome to the mysteries of existence, guys. I'll see you in class.